Welcome, everyone. In this lesson, you will learn to use acid-base titration to determine the concentration of an unknown solution. We're going to use the ChemCollective to precisely determine the concentration of hydrochloric acid. This is the virtual simulation for experiment 17. You can find a copy of the lab instructions in your lab manual, or you can use the link below. So here's the page. Here's the link to download experiment 17 instructions. Then you're going to need to download the assignment worksheet using this link, and then you're going to need the actual simulation itself. Let's take a look at what each of these items look like. So here's the experiment and laboratory instruction for experiment 17. You have introduction. If you scroll down, we'll have list of equipment and chemicals. Then we have the actual instructions. There are 3 parts. And finally, if you scroll all the way to the very bottom, you'll find your traditional report sheet for all of the experiment, and they all look the same. The worksheet that you're going to be turning in for this assignment is a modified version of the actual report sheet. It looks almost the same, except if you scroll all the way to the very bottom, for this assignment, you must include an image of the congratulatory page or the correct answer as proof of completion. If this is missing, you're not going to receive any credit for this assignment. And finally, the actual simulation, if you click on this link, the simulation should show up. Here we go. Using the virtual laboratory, we're going to perform an experiment to determine the concentration of unknown hydrochloric acid solution to 4 significant figures. The concentration of hydrochloric acid and sodium hydroxide are about 0.1 molar and about 1 molar respectively. Solid KHP is provided. Let's take a look at the simulation in the virtual lab. To the very top left corner, we have different tabs. If you click on the Solutions tab, you'll find distilled water, 1 molar sodium hydroxide, 0.1 molar hydrochloric acid, that is our unknown, solid KHP, the indicator phenolphthalein. Under glassware, you have a bunch of different sized Erlenmeyer flasks, starting with 250 ml, and the largest container being 1000 ml. You have several size graduated cylinders. You have several size pipette, a bunch of beakers. You have volumetric flasks, but we're not going to be using them. Under the Other tab, we'll ignore the foam cup and the weighing boat, but we're going to need to use the 50 ml burette. Under Tools, you have a Bunsen burner and a scale. We'll use the scale, but not the Bunsen burner. If you want to bring anything to the workbench, all you have to do is select the tab for that item, click on that item, and the item will show up on your workbench. If you leave too many items in the top left corner of the workbench, occasionally you'll see an error message that says the workbench is full. It's actually not full. It just doesn't like items being placed in the top left corner. So any item you place there, you're going to have the error. So just move it anywhere you want by click, hold, and drag the item and let go, and it'll get moved to somewhere else. Right-click on the item, and you can empty the solid in the item. You can remove liquid from that container. You can also rename the container, and you can also remove the actual container from the workbench. I want to get rid of this from the workbench, so I'm going to remove it. So let's go back to the simulation. The assignment requires 3 items. Experiment 17 instructions, the actual report sheet that we're going to turn in for 20 points, and then the ChemCollective simulation. Let's take a look at the lab instruction. Okay. There are several parts to the experiment. Part 1, we're going to prepare a 0.2 molar sodium hydroxide solution from stock solution. We're going to need to calculate how many ml of a 6 molar sodium hydroxide solution in order to prepare 500 ml of a 0.2 molar solution. In experiment 17, you'll be given 6 molar solution. The virtual lab doesn't have 6 molar. If we go back to the virtual lab, you'll find that under solution, we have a 1 molar solution. We don't have 6 molar. As long as the concentration is larger than what we need, it will work. So let's take a look at the actual calculation, and then we're going to make this after we do some calculation. I'm going to pull up our lecture notes. This is very similar to what we've done in lecture. This time, we're going to prepare a 0.2 molar sodium hydroxide from stock solution. Some things you need to think about before you prepare any solution. How many ml do you need? Will it be enough for the experiment? And what we're going to do is calculate the volume, and the stockroom has 1 molar sodium hydroxide solution, not the 6 in the actual experiment 17. It's a 1 molar in the virtual lab. And we want to prepare 500 ml of it. We as instructors decided this value for you. It's about twice the amount that you would need, meaning if everything goes well, you should have half of the bottle left by the time you are done. We're going to use the dilution formula, M1V1 equals M2V2. The first set of information is going to be the stock solution, the more concentrated solution. The second set of information is going to be for the dilute solution. Let's get some information. The stock solution is 1 molar. What we want to know is how many ml of that stuff do we need in order to prepare a solution that is 0.2 molar, and we want to prepare 500 ml of it. We are solving for V1. Rearrange the equation to solve for V1. V1 equals M2V2 divided by M1. Let's plug in some numbers. Molarity of 1 is 1 molar. Oops, no, I need molarity of 2. We want to prepare a 0.2 molar solution. We want 500 ml of it. And the original stock solution is 1 molar. Let's punch it in. 0.2 times 500 divided by 1. And we have 100 ml. This is only good to one significant figure. That's because we have 1 sig fig here in the 0.2 molar, 1 sig fig there in the 1 molar stock solution. So at best, this is 100 ml. Now we need to describe how to make the solution because we need to actually do it in the lab. In actual experiment 17, we're going to give you a Florence flask. Except there's no Florence flask in the virtual lab. We just need a container that will hold 500 ml of the solution. Let's go find it. Okay, so under glassware, we've got Erlenmeyer's. We've got beakers that we can use. I know they are volumetric flasks, but we're going to not use it. We just need a container to hold about 500 ml. A beaker, while a good container, can't be stoppered and closed. So for practical purposes, I'm going to actually pull out an Erlenmeyer flask, and I need a volume of 500. So click on the 500 ml flask once. It'll bring the item onto the workbench. I'm going to right click on the item. I'm going to rename this container so I know what's in it. And I'm going to call it my 0.2 molar NaOH solution. Click rename, and I'll say there. I'm going to move this item somewhere else. If not, my workbench will tell me that my workbench is full, even though it's actually not. The program doesn't like it when you have items located to the top left corner. So I have an empty container. How do I make this solution? Back to our lesson. To make this, into the container, we are going to add 100 ml of the 1.0 molar sodium hydroxide solution. And the key word here is we're going to add enough water to make a 500 ml solution. For those of you who are doing your math, that means we are adding 400 ml of water. 100 ml of the stock solution plus 400 ml of water to dilute the sample makes the 500 ml. Let's go make this solution. We have a container. Back into the stockroom. Under solutions, grab the base that is 1 molar. To pour anything into a container, all you have to do, click, hold, and drag the item to the container that you want to add to. You'll know you did it right when you move your mouse over that item and that box shows up on the item. That's how you know it's been selected. If you let go, it'll ask you, how much more volume do you want to pour from this solution into this container? There are different features here, what's called the precise feature. There's also a feature where you can deal with significant figures. And then there's the realistic feature where you can click, hold to pour. I actually don't like the realistic feature. I find that it's much easier to deal with, give me 100 ml. I want to precisely pour in 100 ml. So type in 100 ml, click pour, close the window. And what you will see is that the original container with the 0.1 liter of base has now been emptied into this container. This container is now empty. We can remove it. Right click, remove that item. To this container, we need to dilute it with water. Click on the distilled water. Click, hold, and drag the item over to your flask. You know you did it right when you see a box being highlighted on the item you want to pour it into. So if you move the mouse left and right, you'll see that the item is selected. Let go. Okay. And it'll ask you, how much water do you want to pour in here? We've been doing our math. 100 ml of the stock solution plus 400 ml of this water. Click pour, close this item out, and get rid of this water. To the top right-hand corner, you now have made a 0.2 molar sodium hydroxide solution, and we got 500 ml of it. Guard this solution from the very beginning to the very end of your experiment. If at any point it's spilled, it's empty, it's discarded, it does mean starting your experiment all over again. So that ends the first part of the experiment. Part 1, prepare the 0.2 molar from stock solution. And our stock solution is not 6 molar. The virtual lab gives us 1 molar. Do not discard the solution until the entire experiment is complete. If you forget this or made a mistake, you do need to start over. Part 2, let's standardize the solution that we made in part 1. You're going to need a burette for this. When you pick up a burette, you need to clean it. You're going to clean it with deionized water. You're going to rinse it with 10 to 15 ml portion of the solution you just made before you put it in. That's because when you clean a burette, it's actually wet and there's no way to actually dry it. So the way to get the solution in without changing its concentration is to acclimate or to prime your burette. You've seen that in the video. The thing about this is that in a simulated program, we're going to presume all instruments are clean, primed, and ready to go. We don't need to do any of that because it is a virtual lab. In the stockroom, under the glassware, under the other, grab your 50 ml burette. It is clean, it is primed, it is acclimated. We don't need to do any of that in the virtual lab. For the actual experiment 17, you do. Then it's going to give you different instructions so that you can actually learn how to use this. Let's go back. Okay, so here's a little bit of instruction on how to read a burette. Eyes to the level of the burette. Okay. Let's see. Let's fill the burette with the sodium hydroxide that we are going to use. And we're going to read the burette by estimating to the 0.01 milliliter. Okay, so we got our burette, we cleaned it, we primed it, we acclimated with this sodium hydroxide solution. It is now time to fill it. This burette holds a maximum of 50 milliliter. The 0 marking is up here at top. The 50 ml marking is here on the bottom. If we want to fill it with anything, we're going to click that item, click, hold, drag that item over to the burette so that the burette is selected. And you know the burette is selected when you see that box surrounding the burette. Let go, and it's going to ask you, how much do you want to fill in here? I know on my screen it may not be very apparent, but there is a little box right down here. This little box is to help zoom in on the measurements of the burette so you can actually read it because these markings are really tiny. So there is a zoomed in image of the burette and that little box is going to move where it is. It's going to hold 50 ml. So you can fill it all the way to 50, a little bit over 50, but you're going to have to drain some of it. So I'm going to start with, say, 45.6 ml. It could be any quantity below 50. I'm going to click pour. And when I click pour, that little box jumps up all the way to the top of the burette. And the zoom in image shows me that the burette has been filled between 6 to 7 milliliter based on the markings of the burette. So up here are the small measurements. Down here are the large measurements. I'm going to close it. I'm going to save this solution in the top right corner. I now have the burette filled and ready to go. You'll find that in the actual instructions, there's a bunch of other things you need to do to it, but in a simulated program, we're not going to do much. Okay. It says read the burette as your initial measurement. So we're going to do that in a little bit. Okay. Then it asks us to measure out 3 samples. That's because we're going to do the titration 3 times. Trial 1, 2, and 3. Laboratory instructions says we're going to use anywhere between 1 to about 1.1 gram. Don't go under 1 gram. You can go over 1.10 gram. Try not to go over too much. That's because the more KHP you use, the more of the base you're going to need for this experiment. So don't go under 1. You can go over 1.1, and you certainly I wouldn't go over 1.5, honestly. Okay, so between 1 to 1.5 for your experiment. If you go back to your actual assignment, the sheet that we're going to fill in, I gave you 3 trials and then I even gave you a 4th. What we're going to do is record 3 trials. So for this one, for trials 1, 2, and 3, including 4, you're going to use 1 gram, 1.1 gram, 1.2 gram, and 1.3 gram respectively. What I want is for you to weigh out different quantities. And that's because in reality, when you weigh something out, it's not going to be the perfect mass, the same mass every single time. It's going to show up a little bit differently each time. So for each trial, you're going to have a different mass. In a simulated program, it's easy to set out 1 gram, 1.1 gram, 1.2 gram, 1.3 gram, and so on and so on. So let's go back to the simulation. Okay, I'm going to move my burette to the side, go back to the stockroom, under glassware, under Erlenmeyer. I'm going to grab 3 flasks. Click it 3 times. 1, move that item, click it again. That's 2. Go back, click it again. Or you can click another one and then have a 4th child. So 4 different flasks for this experiment. I'm going to place them at the very bottom of my setup. And I'm going to label these flasks so that I know which trial belongs to which flask. Right click, rename. I'm going to call this trial 1. Second flask, I'm going to call it trial 2. Third flask, I'm going to call it trial 3. And if you want, you can do trial 4. Okay. Back to our instructions. It says measure out 3 samples of KHP into 3 separate Erlenmeyer flasks. In the lab, you got a 125 mil. In the simulation, we got 250 mils. It's just a container. Don't worry about it. Let's go weigh out our KHP. Under the tools, grab a scale. Okay. To weigh an item, click, hold that item, and place it on the scale. Let go. And it will tell you the mass of the empty flask. I'm going to go back to my report sheet, the version that I created for this assignment. And you know you got the right version when you see the word titration in the top left corner. And at the very bottom, okay, an instruction to include proof of completion. So the mass of the flask, type in and record the mass for that value. I got 101.9178. Okay, 101.97, what was it? 9178. Okay. Then I want to record the mass of the flask with KHP. And for trial 1, I'm going to use 1 gram. For trial 2, I'm going to use 1.1 gram. For trial 3, I want to use 1.2. Trial 4, another mass, respectively. So to get the KHP in here, I'm going to go back into the stockroom. Under solution, at the very bottom, not quite bottom, is KHP. Click that once. The solid bottle shows up. Click, hold, and drag the bottle over to the Erlenmeyer flask. Not the scale, not the other beaker, not that. Hover it over the flask, let go, and it's going to ask you, how much do you want to transfer over? We agreed 1 gram. So I'm going to type in 1.0 gram. I'm going to click pour. And you will find that the mass has increased by exactly 1 gram. That's not usually the case in the lab, but it's a simulated program. Close it out. I'm going to leave that there. I'm going to go back to my worksheet. I'm going to record that mass. It's now 102.9178 gram. Okay, so 102.9178 gram. I'm going to remove that flask. I'm going to put the second flask onto the scale. For this tutorial, I'm only going to do 2 trials. You can do trial 3 and 4. Here, I'm just going to do 2 trials, just to show you how to work the simulation. So for this second trial, the mass is 100.9661. 100.9661 gram. And for trial 2, I'm told to use 1.1 gram. Click the KHP, move it over, click, hold, and drag, select the flask, let go, and I want to put in there 1.1 gram. Click pour, and I record the new mass as 102.0661, 102.0662 gram. Okay, as the mass of the flask with KHP. And you can do that for trial 2 and trial 3 and 4, and so on and so on. So what it means is that I can calculate the mass for each trial. Take the container with the flask, take the mass of the flask with the KHP minus the flask, and we will have 1.0000 gram for the first trial and 1.100 gram of KHP for the second trial. Okay, now we are ready to titrate. If we go back to experiment 17 instructions, okay, so we measured out 3 samples. It says dissolve the crystals with 25 ml of DI water and add 3 drops of phenolphthalein to the flask. Okay, so I'm going to take this down. I don't need the KHP and I don't need the balance anymore. Right click, remove the item from the workbench. Okay, so I'm working with trial 1 and trial 2. Trial 3 and 4 are completely empty. There's a white spot in the flask indicating there are some solids in it. So into the solution, we need to add 25 ml of water to dissolve the solid. Click, hold, and drag the water into the first container. It's going to ask you how many of that do you need to pour. We're going to add in 25 ml, click pour, close it out. Then do it again for trial 2. We're going to add 25 ml, click pour, and we are done with adding the water. Remove water from your workbench. And finally, we're going to add the phenolphthalein. The lab says 3 drops, and you want to stay consistent. It will work with 1 drop, 2 drops, 3 drops, 10 drops. It actually will work with any quantity you want, but be consistent. So if you use 3, use 3. If you use 4, use 4 for all trials. There's no way to get 3 drops from the simulated program. So what I'm going to do is click, hold, and drag the item to the flask, and I'm going to estimate the volume of 3 drops, and I guess 0.3 milliliter. That would be my guess for 3 drops. That's because I can't actually use the drop and click it. I'm just going to pour 0.3 milliliter from the phenolphthalein to the container. So I'm going to click pour. I'm going to close it and then do it again for the next trial. So my guess would be 0.3 ml for 3 drops. Click pour. Now I'm done with the indicator. I'm going to remove that. Okay. Now if you want to do all 4 trials, now's a good time to prep all of your flask. What I'm going to do is go back to the instructions. Here we go. Measure out 3 samples of KHP, anywhere between 1 to 1.1 gram. Dissolve the crystals with 25 ml of water. Add 3 drops of the indicator. Now we're ready to titrate. We're going to place the flask under the burette We recommend a piece of white paper so that it makes it easier for you to see the pale pink color. And then we're going to start titrating. The instruction for titrating is right here, okay? So it's a little different than the actual simulation, but you'll get the point. So how do we titrate? What we want is for the content of the burette to mix in with the content of the flask. But before we start, we need to record the initial burette reading. That way we could figure out what volume of the base goes into the flask. And we lost that zoomed in image on the burette. So to get it back, you want to right click on the burette and it'll tell you a detail view. If you click on that, it will show up with a little box up in the top. If your box is all the way on the very bottom, by the way, that's because your burette is empty. You need to fill it with something. So if you filled it with something, it would show up somewhere between 6 and 7. So we're going to read what is called the initial burette reading. We're going to read it upside down, not right side up. So this is 6 mil. This is 7 mil. Each of these increments is a 0.1 mil, and we are at 0.4. There's a space in between the increment. That's the guess. That makes it 1/100th of a mil. If it's dead on the line, we're going to add that extra 0 at the end to ensure 3 sig fig. This would be 6.40 milliliter as the initial burette reading. So back to our report sheet, or the sheet for this experiment. For the initial burette reading, I have 6.40. Don't forget to add that 1 extra 0. Then we're going to take a look at the final burette reading, and we do that after the solution turns pink. We're ready to titrate. So what we want is the content of the burette to go into the flask so that the solution turns the lightest pink as you possibly can. So I'm going to click, hold, and drag the item to the container, to the flask. So I want you to pay attention to the tip of this mouse. If it's really close to the bottom of the burette, if you click, hold, and move it over to the first flask, you'll notice the square box being selected, okay? And if you let go, it'll start to ask you to do the titration. The problem here is watch the mouse, watch the tip of the mouse. Some students hold the burette from up here. If you hold the burette from up here and you click and hold, if you keep moving it down, notice there's no highlight on the flask. That's because the tip of the mouse is on top of the image. So you actually have to go all the way down, keep moving this down until the tip of the mouse touches that flask. And that flask is highlighted when you see that box on that flask. So a lot of students they'll move like this, and they will make sure the tip of the burette is right above the flask, right? In the lab, that makes sense. But in a simulated program, if the two items are not selected, it's not going to work. So the tip of your mouse matters. So if it's close here, if you touch it, it's right there. But if your tip of the mouse is up here, you click, you have to like drag it down, 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 down until it's actually selected. If you let go, it will rearrange itself into the proper setup. Here's the problem. The first trial is going to be really tough. You don't know where the endpoint is. You don't know what volume you're going to need. So oftentimes we professionals do what's called a quick and dirty trial. We actually move very rapidly until it's sort of there. So, and that's what I'm going to do here. I don't know exactly where it is, and I'm impatient. I want to know roughly where the answer is, where the endpoint is. So instead of going drop by drop by drop, which is incredibly tedious, and I don't know where it is. I don't know how long it's going to take. What I'm going to do is be aggressive. There is a precise feature, and then there's a realistic feature. the realistic feature makes more sense. If you click and hold to pour, you'll see the meniscus keep dropping. So I'll show you right now. I'm going to click hold to pour. And notice it went from 6.4 to now 6.8 something. So if I keep clicking and holding and pouring, I will have drained the solution rapidly into the container. And this is not very good. We're not going drop by drop. We're going quite fast, actually. And I'm going to keep going. And I know I'm going to over titrate because I'm going too fast, and that's okay. I just want to know where the endpoint is. And I'm going to keep on going until the solution turns pink, and then I'm going to stop. So I'm about at 31. I should be almost there. There you go. So I just click hold and the container just turned pink. And I know I over titrated, and I know I wasn't careful, and I know I wasn't trying to get a drop of it to turn the solution pink, but it's good enough. It's what I call my quick and dirty trial. The pink signals the end of titration. We're at the end point or the equivalence point, and I'm going to read the final Biuret reading. And between 33 and 34, it may be different for you. It's dependent on your version of your program. So I got 33.12345.6. I got 33.6, and I'm going to take a guess in between that space. The standard guess is a 0 or a 5. I think I can do a little bit better, maybe an 8. So 33.6. And I guess 8 milliliter. To calculate the volume of sodium hydroxide used, I'm going to take 33.68 minus the initial Biuret reading, and I'm going to get the volume that is now sitting in this flask. So let's do some calculation. Take 33.68 minus the 6.40. And for my version, I have 27.28. I need to let you know that every time you start this program, it's going to be slightly different. The unknown is different. The solution is a little different. So if you're trying to match the final Biuret reading for me, it will not be the same. That's because my version may be a little bit different than yours. That's because every version, every time, it's sort of like that homework problem when I give you, every time you restart, it's not exactly the same number. It's going to switch the number up over and over again. So your endpoint, your equivalence point may not be where mine is. Then we need to convert this volume into liters from milliliter. So take 27.28 divided by 1,000, that's 0.02728 liters. The rest of this is going to be calculation, and we're going to do just that. Okay. So here is the information that we were looking for. We have the mass of the flask, the mass of the KHP and the flask, the mass of the KHP by itself. We dissolved it in water. We add the water. Then we added the phenolphthalein, and then we added the base, and we finally calculate the volume of the base. So what we're going to do is show you how to do the calculation. So we made the solution. The molar mass of KHP is 204.22. Here's the calculation. We were given 1.000 gram of KHP. You should have the same number as I do unless you weigh out a different mass. The goal for this part is to determine the molarity of sodium hydroxide. Molarity of sodium hydroxide is defined as the moles of sodium hydroxide over the liter of the solution. The bottom part comes from your titration data. That's the part where we took the final volume of the burette reading minus the initial burette reading. It's going to be in unit of milliliter, so don't forget to convert it to liter. The top portion requires stoichiometry. We started with our primary standard. We weighed out 1 gram. We're going to convert it to the moles of KHP. We're going to calculate the moles of sodium hydroxide, and that value is going to go there. So let's do some calculation. Molar mass of KHP is 204.22 grams for every 1 mole of KHP. As a reminder, this is the abbreviation. So the KHP here versus this, they're meant to be the same thing even though they're not. So KHP is the abbreviation for this chemical formula here. To calculate the mole of sodium hydroxide, we use stoichiometry, 1 mole of KHP for every 1 mole of sodium hydroxide. Then we plug it in. Take 1 divided by 204.22, and in 5, and that's 5 significant figures. Yeah, it was 4 numbers after the decimal place for this scale. So I have 0.004896. I'm going to round it off to 5 significant figures. So 245. If you want to carry 1 extra sig fig, you can. I'm just going to stop there. So that's moles of sodium hydroxide. Then we're going to plug it in. 0.004967 mole for every liters. So I forgot what the volume was. So let me go back and get that number. It was 0.2728. So it's 0.2728. Take the answer, divide it by 0.02728, and the molarity is 4 significant figures, 1795 molar. Did we do it right? Sorta. Okay, remember we made a 0.2 molar sample, and this number sorta came close. I know I over-titrated, but I'm pretty close. So that's the calculation for the first trial. Okay, so you should have been able to calculate the moles of KHP, the moles of sodium hydroxide that reacted, and then the molarity of sodium hydroxide. So we did all 3 of these calculations. That's the first trial. The problem with the first trial is that I know I over-titrated. I went rapidly. I wasn't very careful. I just want to roughly know where it is. I used 27 ml for the first trial that requires 1 gram of KHP. The trick to this is that if you weigh out 4 samples, you want to line them up in increasing mass. So ideally, you want to start with the container that has the lowest mass. And what it means is that it would require the lowest volume of base, so that as you increase the mass, the volume of the base would also need to be increased. But I know I over-titrated here. So strategy-wise, if I start with the small amount and I keep increasing, I expect the volume to keep increasing. So what it means is that I'm going to go a little faster in my second trial. So back to my titration. A lot of students say, can I just continue to the second titration and not refill my burette? The answer for this is no. Right now, my burette is only about halfway full. I know that I need about 27 mil, and I've already used more than half of it. So if I continue using this, I'm actually going to run out of solution. So I actually need to refill my burette, and that's what I'm going to do. Grab the base, click, hold, and drag it over to the burette, let go, and it will ask, how much do you want to add? Okay, I've got 34. Okay, and I want to fill it all the way up. This is a 50 mil burette. I used about 27 mil. So maybe I want to pour in about 25.78 mil, or any random number that is a little under what I used in the previous trial. So I used 27 mil from the previous trial. I'm going to reload that amount into the burette, and I'm going to pour. So now I'm back up a little under. Maybe I want a little bit more. If you really want to start with a full burette, maybe add another 4 mil, click pour. I'm now between 3 and 4. I'm good. I'm not going to try to get it to 0. That's really not the point. Okay. Now my burette is full again. I'm going to read the initial burette reading for the second trial. I'm at 3. It looks to me like 8, and I'm really close to the 9. So I'm going to go 3.89 as that my initial burette reading. Yours might be different. You may fill it to any quantity that you want, and then you can start there. Just make sure your burette is full again. And you can tell that it's full if there's a box on the very, very top, and the zoomed in image have markings that are really small, close to 0. So anywhere between 0 and 10, and your burette is roughly full. So, right, initial burette reading. I know for the first trial using 1 gram, I used 27 mil. So I'm gonna use this and not go drop by drop because I roughly know where it is. What I'm gonna do is I'm gonna go rapidly, and I'm gonna pour in all like 20 mil all at once. And hopefully it doesn't turn pink on me. So click, hold, and drag the burette into the second container, the second trial. And under the precise volume, click, hold, and drag. Under the precise volume, I'm going to go rapidly. I'm going to fill in 20 mil to start, and I'm going to click pour, and it should not turn pink, and it did not turn pink. Now I'm going to slow down. When I slow down, I'm going to go drop by drop. But 20 mil is not close. I've got 7 to go. So what I'm going to do is go a little closer. So you can change this volume to go in tiny increments like 0.5 mil. And if you click pour, notice that it's moving much faster, and that's still too fast. I'm going to slow it down even further to 0.1 mil. This is about a drop or 2 equivalent. I'm going to click pour. I'm going to click pour. Notice that it's moving in tiny increments now, about a 0.1 mil. You can go even smaller than that to 0.5. This is not the equivalent of a drop or half of a drop. Click pour, and you'll notice it goes a lot slower. And you're going to keep clicking until one click turns the solution pink and stays pink. So I'm going to stay at this increment. I'm happy with it. It's small enough so that I don't go over and over titrate. And I know I need about the same amount, if not more, than the first trial because I have more mass of KHP here. I'm almost there. Almost there. I'm at about the same volume as before. And I need one click to turn it pink. And this time I'm much more careful than my first trial. There you go. Notice how much lighter this pink is compared to that pink. For my colorblind students, I apologize. I know you see contrast, and the gray here is a much lighter gray than the first trial. This is because the second trial, I go a little slower. I anticipated the endpoint. I know roughly where it is, and I slow down, and I want one drop to turn the solution pink and stays pink. So with each trial you do, it's going to get a little bit better. I'm going to read now the final Biuret reading at 33.89 would be my guess. 33.89. That means the volume of sodium hydroxide is going to be 33.89 minus 3.89, and that gets me 30.00 milliliter for the volume that I need. This kind of makes sense. In the first trial, I got 1 gram. I used 27 mil of the base. If in the second trial, I increase the mass, logically, I need more base to react with it. So I have 0.03000 liters for the sodium hydroxide use. I'm going to do the same thing, and I'm going to calculate the molarity for the second trial. I got the molarity for the first trial as 0.1795. And I'm going to do the same calculation for the second trial. So take the 1.1 gram of KHP. We're going to divide it by the molar mass of KHP at 204.22. And I have calculated the moles of KHP used. The mole-to-mole ratio is a 1-to-1. And then I'm going to follow the calculation, and I'm going to calculate the molarity of sodium hydroxide for my second trial. So you can pause the video here, do your calculation for your second trial, and then compare the compare the two trials. I'm going to do that for my number now. And I have 0.1795. Oh, how odd. It's almost exactly the same. I got lucky. Okay, I got really, really lucky. So it looks like the first trial and the second trial are really, really close. No change there. I'm going to double check my numbers. 1.1 divided by 204.22 divided by 0.3. That's 30 mil. Yeah, I just got lucky, you guys. Usually my molarity for the second trial is very different than the molarity of my first trial. And this will not be your, this here will not be your case. So when you're done, you're going to do this 3 times or 4 times should you choose. So what you'll find is that usually your first trial is a drastically different number than your second trial, then compared to your third, and then compared to your fourth. So what you're going to do is take the average molarity of your best trials, and usually it is not the first trial. It's usually the subsequent trials that are your best trials. But it looks like I just got lucky, so my molarity is going to be average at 0.1795 molar for my base solution. Yours might be a little different, but it should be about a 0.2 molar. This ends the first part of the experiment. And for most students, you're going to stop here on the first day, and then you're going to continue on with the second day, okay? So you're going to store your solution, and then you're going to come back and finish part 2 for the second part of the experiment. So here in the simulation, we can just keep going. Okay, I'm going to close that out. Let's clean up these flasks. I'm done. So I'm going to remove the items from my counter. Okay, I didn't do trial 3 and 4, but you can. So this here is no longer 0.2 molar. So if you stop at this point, you've calculated 4 trials and you have determined the molarity of sodium hydroxide. So we're going to rename this. Right click, rename this, whatever yours is. Mine is 0.1795 molar. Okay, good to 4 significant figures. So it's no longer a 0.2 molar. It is now a 0.1795 molar solution. My burette still holds my base. I'm not going to empty that. Let's go back to the lab instruction. Okay, we are now done with part 2. Part 3 is to determine the concentration of hydrochloric acid. It asks you to prep the burette again if it's your second day, but if you continue on, you actually can just continue on. Obtain an unknown. Clean a 25 ml volumetric pipette, and we're going to prime and acclimate the pipette with 5 ml portion of the unknown solution. And this one says do it 2 times. I'm slightly on the neurotic side. When I was a student, I was always doing them 3 or 4 times each. That's because it's really hard to clean a pipette and make it dry. So what we normally do is we rinse the pipette with the solution that we're going to put in it so that the concentration doesn't get changed because of the water sitting in it. So we're gonna go to the virtual lab. Okay, so virtual lab from the stockroom. Here is our unknown under the solution. Click on that. So here's the unknown. The unknown is about a 0.1 molar. Already we have it to 1 sig fig. Our goal is to get it to 4 sig figs. From the stockroom, under the glassware, grab a pipette. We're going to need the 25 ml pipette. Okay. Last time I did this, the simulated program kind of sucked. It didn't show me the zoomed in image, but hoping that it works this time. Grab a flask. You're going to do this again 3 times. I'm actually going to only do it once. So you're going to do it 5 times. So you would need to prep 3 flasks 3 single time. I'm just going to do it once. I did it twice for the first part. I'm only going to do it once for this part. So I'm going to label this trial 1. Okay. For all trials, we're going to transfer 25 ml of this acid into this container using this pipette. That is because if we try to take this container and pour it haphazardly, we're not going to get precisely 25.00 milliliter. We're actually going to get something not very precise. A graduated cylinder won't work here. And if you imagine a graduated cylinder, when you pour in a liquid and you pour it out to a container, there will be liquid left over in the container. So it's actually not a very good way to transfer solution. But this tool right here, a pipette, is designed specifically for that. It's calibrated to deliver a specific volume from one container to the other. So from the pipette, I'm going to click, hold, and drag it over to my unknown. Okay. And because this is a realistic program, I'm going to first withdraw. And by the way, that should have said 25, not 5. Okay, so that there's a little box right here. That's my calibration mark. So the simulated program is a little wonky here. That should say 25, not 5. So I'm going to first withdraw 24.5. I'm not going to quite there. I'm going to withdraw. And yeah, no, that did not work, you guys. This meniscus is not working. So I'm going to empty the liquid from it. I'm going to try again. I'm going to put in exactly 25 and see if the simulation works. Yeah, no, it's not working. Remove liquid. I'm going to try once more. Yeah, this is not working. Maybe I'm going to do sig fig 25.0, withdraw. Yeah, no. What you're supposed to see is you're going to withdraw. There's a meniscus along this line so that the bottom of the meniscus hit this calibration mark. So it looks like they didn't fix the simulation here. They just, yeah, it worked before, but it's not working now. But you get the point. You've used a pipette before. You're going to draw the liquid up so that the bottom of the meniscus hit this calibration mark. And what I'm going to do is take this, move it over to my container, let go, and then I'm going to pour out exactly the 25 ml that I'm supposed to have. I'm going to click pour, precise 25.0. I'm going to pour. There you go. Okay, so now I have 25 ml of my unknown in here, and I took that from this unknown container into trial 1. And if you run out, you can actually grab more from the stockroom. This won't be the case in the actual experiment 17 because each student gets 100 ml. You're not going to get more than 100. So if you run out, you're actually going to need your instructor to give you another sample. Okay. From the stockroom, don't forget your phenolphthalein. Add 3 drops. I estimated 0.3 ml for 3 drops. I'm pretty sure my estimate is wrong depending on how large or big the drop is, but good enough. I'm going to stay consistent. Okay, and I'm done with my phenolphthalein. I'm going to get rid of it from the desk. I'm also going to move the pipette to the very right corner. And now I am ready to titrate. So go back to the lab instructions. The lab instruction tells you to clean your pipette, prime or acclimate your pipette. Then it's going to show you to deliver and transfer 25 ml of the unknown acid solution. In class, your instructor will definitely demonstrate this. They've actually already done this in experiment 1, but I'm hoping they'll do it again for you. If you need help, please ask. Add 2 to 3 drops of the indicator. We just did that. And then start titrating until the color turns pink at the endpoint. So here we go. Click, hold, and drag the burette and place it right above trial 1, the flask. But here's the thing, I am empty again. I used about 27 ml of it and I want to reload. So grabbing my base, I'm going to refill my burette every single time. So I'm going to replace 27 ml, the volume that I used. And now maybe another 5 ml, 5.32 ml. Just so I'm up there somewhere. Okay, I'm happy with that. My burette is filled. I'm between 1 and 2. I'm happy with that. So I'm going to start titrating and I'm going to read my initial burette reading. I'm between 1 and 2, so that's 1.1234. And my guess is probably an 8, 1.48. So back to the report sheet. For all trials, use 25 ml. What happens is that if you need trial 4, you actually need to use less. Use 10 ml. That's because you're going to run out. So for trial 1, it's 25 ml. For trial 2, it's going to be 25 ml. For trial 3, it's going to be 25 ml. And what happens is when you get to trial 4, if you want to do trial 4, you're not going to get enough. So you're going to have to use 10 ml. If you're going to use 10 ml, you're going to have to ask your instructor for a different pipette, and they may or may not give it to you. So if I'm your lab instructor, please ask, I'll bring out the 10 ml. If something goes wrong with one of these trials, I'll make it work for the 4th trial for you. So initial burette reading is, for me, 1.12348. 1.48 mil. And I'm going to start titrating. Okay. I can go realistic. I can hold to pour. And the problem with the first trial is that I don't know where the endpoint is. So trial 1 could be your quick and dirty trial. You can do tedious. You can do like 0.05 mil and just keep clicking in tiny, tiny, tiny quantities until the solution turns pink. That can be very frustrating because it will take a long time. I'm aggressive. I go by 1 mil. And that's because the first trial is my quick and dirty trial. I just want to roughly know where it is. There you go. Okay, I know I over titrated and that's okay. I can go back and fix it in my second trial. I'll be a little bit more careful in my second trial. So I've got 16.49 as the final burette reading. 16.49 mil. So that the volume of sodium hydroxide solution used is 16.49 minus 1.48. And we got ourselves 15.01 milliliter, or 0.01501 liter. The standardized molarity, this is the average from the table 1. So from table 1, we spent all that time to calculate this molarity. So we're going to need it now. And that goes here for all trials. Then we're going to do some calculation. So let's do that. Okay. So here's the data collection for part C. The volume of acid that we asked is you're going to dispense out 25 ml using a pipette. And this is for all trials. I've got my initial burette reading. I've got my final burette reading. I've got the volume of the sodium hydroxide used by taking the final volume reading minus the initial volume reading. And then I'm going to use the standardized molarity in order to do some calculation. Let's do some calculation. The goal of this part is to determine the concentration of hydrochloric acid, and this simulated program will give us 4 significant figures. We made a solution of sodium hydroxide that is standardized to 0.1795. I believe that's my value. Yours might be different. We can now use the standardized solution to determine the concentration of the hydrochloric acid solution. So the goal of this part is to determine the molarity of hydrochloric acid. That's moles of HCl over liter of this solution. The bottom piece comes from the experimental instruction. We asked that you use the 25 ml pipette to dispense this quantity. Don't forget to convert it to liter. We have volume of sodium hydroxide. And for me, that was 15.01 mil. This one comes from titration data. That's the V final minus the V initial. So from the volume of sodium hydroxide, I'm going to use the molarity, that's 0.1795. That's moles of sodium hydroxide per 1 liter of this solution. We're going to start with the volumes of sodium hydroxide. We're going to multiply it by its molarity, and we can use the mole-to-mole ratio to calculate the mole of hydrochloric acid. Let's do that. We have 15.01 mil, or rather, we need to convert that to liters, 1,000 mil for every 1 liter. Then we're going to multiply it by the molarity, 1 liter of this solution. The molarity is 0.1795. That's moles of sodium hydroxide. The mole-to-mole ratio is a 1-to-1. 1 mole of sodium hydroxide for every 1 liter of this, 1 mole for every 1 mole of HCl. Let's punch it in. 15.01 divided by 1,000 times 0.1795. And I have 0.002694 moles of hydrochloric acid. And I'm working in 4 significant figures. So for the formula, I'm going to plug that in. Molarity of HCl is equal to 0.002694 divided by the 0.02500 liter. It has to be in liter, not milliliter. That's moles on top, liter on the bottom. And I have in 4 sig figs 0.1078 molar for the unknown. Did I do it right? Sorta. The program tells me that it's about a 0.1 molar, so I'm close. I just need it in 4 sig figs, not 1. Okay, if that's the case, let's take a look at it. So I was able to calculate sodium hydroxide moles, that's volume times molarity. I was able to calculate the moles of hydrochloric acid, and now I have the molarity of the acid at 0.1078. The question is, how do I know I did this right? I actually don't, and this is why we have trial 2, trial 3, and trial 4. The nice thing about using the same volumes of solution for all 3 trials is that the volume of the base should roughly be the same. And what you'll see is that you get better at titrating, so the volume actually gets smaller and smaller as you refine each trial. So if I were to do this again, this volume I would expect to be less than 15 mil and then even a little less than that of it. But let's say I think I'm done. I think this is the molarity of my unknown. All right. And I want to know if I'm right or wrong. Okay, so this is the part where I just want to turn in my report and I want to be done with the assignment. So this program has an auto-graded function. It asks, what is the concentration of the unknown hydrochloric acid solution? I'm going to type in a value that is not my answer. So I say it's 0.1342. Okay, it's not my answer, just so I can show you what a wrong answer looked like. I'm going to click check. And it says, you are wrong, but you still have 2 attempts left. What it means is that the program only gives you 2 shots at typing in your answer before it shows you the answer, and then you're forced to turn in the assignment. So I'm going to type in my answer, and I know it's not right because in trial 1, I over-titrated, so it's 0.1078, and see if that's correct. Click check. You are wrong. You still have 1 attempt left. So I know I didn't do it right. And so what I want to do is just do 1 more trial, knowing that I used 15 mil. So back to my simulation. I'm going to do this just once more. Going to empty that container, grab another Erlenmeyer. I'm going to use my pipette, grab 25 ml. Then I'm going to transfer that into my flask. I'm going to withdraw exactly 25. And then I'm going to need my indicator again. And I'm going to put in 3 drops. 0.3 would be my guess at 3 drops. Okay, and then I'm going to titrate. Here's the thing. Do I need to refill my burette? The answer is actually no. That is because I used only 15 ml. This thing holds about 50 ml, and so I know I have a little bit left. So my initial burette reading is actually the final burette reading from the previous trial. So I got 16.1234. So for my trial 2, it'll be 16.49 as my initial burette reading. And I already have an answer right here. I used 15 ml, and I know I went a little overboard, so I'm going to go a little under that. I'm actually going to go to about 14 ml first, and then I'm going to slow down. So I'm going to rapidly add 14 ml to start. Oh no! And that was too much. I definitely over titrated, so I better do that again. That was bad. I over titrated. Let's do it again. So it's definitely less than 14 then. I'm going to need probably maybe 12 and then I'll slow down. So let's grab, I think I'm almost out. Yeah, I'm out of acids. I'm going to grab more. So there's more of my unknown. Grab a pipette, draw out 25 ml. Transfer it to my flask. Withdraw 25. Okay, add some phenolphthalein. 0.3 ml. Okay, and then I'm going to now titrate. I'm at 30 so it looks like I have 20 ml left here. So I should be more than enough to do a third trial. So 30.48 as my, so I'm gonna discard my trial 2. 30.48 is my starting for trial 3. 30.123448. And then I'm gonna be rapid again because I'm gonna go 13 ml first, and I hope it doesn't turn pink on me. Okay, then I'm gonna go in tiny increments, 0.05, and then I'm going to keep pouring in tiny quantities until it turns pink. There it goes. I think I might have like clicked once, one too many, but that's okay. So I got 40.42 as the final reading. 40.42. Let me double check. 44.42. Yeah, 44. And then let me see how many mil that is. That should be 14 point, nope. 44.42 minus 30.48. And I have 13.94. Okay, so notice my first trial, I went over by a good mil. This one, I'm a little under, so I'm gonna recalculate the molarity and the volume of my base. So 0.01394, and I'm gonna see if I can calculate a new molarity. So 0.01394 divided times 0.1795 divided by 0.25. And my new molarity is actually 0.1000. Oh, I'm a lot closer. So I'm going to test this number in the simulation. Hopefully I'm right, but if it isn't, I do want to show you what the end looks like. So 0. And I have only one attempt left. I'm going to click check and I'm done. Okay, so it looks like I did it right the third time. And if you did it right, it will show this. Good job. You have successfully identified the concentration of the hydrochloric acid solution. So if you get this page, you need to enter this page into the simulation, into your assignment as proof. So I have an Apple product. So Control Shift 4, and I will be able to capture the screen. Okay, so it's right here and it's a screenshot. So I'm going to copy this page and I'm going to paste it onto my Word document as proof that I'm done with the assignment. So here is my proof. Right, so there's my proof and I am done and I'll get the 20 points for that. What happens if you don't get it right? The program basically wipes your work and you have to start all over again. And every time it starts all over again, it actually gives you a new acid unknown. So just like if you run out of your solution, you actually have to start over, and that will be true for this program. But don't despair. I grade based on a curve. If you don't get the congratulations page, it'll tell you you didn't get it correct. However, here is the correct answer. If you don't feel like doing it again, you can still turn in your assignment. You just don't get full credit for it. So let me show you what your grading rubric looks like. If you got the full congratulatory page and 3 out of the 4 sig figs are correct, you get full credit. If you have 2 of the 4 sig figs correct, you get a B for the assignment. And if you only get 1 sig fig out of the 4 correct, you'll pass. You'll get 12 points for the assignment, and then that's it. So it can be frustrating, but you can redo the assignment if you just can't get it right the first time. Okay, so be patient with it. You're basically doing experiment 17 using a simulation. If you have questions, please do not hesitate to ask. Please come to my office hours. I will show you, and then I can hold Zoom sessions to help you with this, because it's actually really easy to hold Zoom session and show you how to get any of these done. So please let me know if you have any questions. This ends the tutorial, and then we're going to do the actual experiment when we are done.